Hello, everyone. How is your day today? We have several things to announce. The first thing is we have quiz on Thursday. Okay, so it takes like 10% or 50%, 15%, right? Uh, One quiz. I do you need more? If you need more, we can have more quiz. Okay, so we announced the range of the quiz every sections after midterms and end of today. So that will be all these questions comes from. Okay, I hope you prepare well. No, no, Okay, and then for our course video, actually TA help us to improve the video qualities. So what they did is they extract the soundtrack and then they transform the script from sound to text. And then they use my own voice to regenerate the sound clips. Before that, they try to correct the grammar and use the corrected sound clips back to the videos. So all of this process was generated by different AI tools to help us to improve the quality. For example, the balance of the volume. Then you can maybe see the video with very clear sound. Okay, I hope you enjoy the video clips and help you to understand the course content after class. All right. Today I'm going to introduce section 10.5. It is Euler in Hamilton graphs. So we will see Euler path and Euler circuit and Hamilton path and Hamilton circuits and different applications in this section. Okay, so firstly, let's see what is Euler path and circuit. So the story back to seven bridge problem because there's a little town in Russia just look like this. They have four different sections and different sections was connected by different number of bridges. For example, the section A connects to section B by these two bridges, and coming by C with two bridges. So people start to ask one question: can we visit every section using this bridges just once? Okay, I think that's the problem often asked by the tourists, right? Because they want to travel different bridges and they want to save time. So they just want to travel the bridges exactly once at the bridge. Okay, and the mathematician tells us there's no way we can visit every bridge once and form a path. Okay, so later on we'll see why seven bridge problem cannot be solved. So we call this Euler path and Euler circuit problem. We have introduced the definition of path in previous sections. So we know what is a path. Okay, we can express the path by a sequence of vertices, for example, x0, x1, x2, x3, xn. And each vertex travel along the path E1, E2 to En. And that gives us a path. So what is a simple path? If there's no repeating edges in this path, then we call this a simple path. So if we travel from x0 along the path and back to x0, then we call Okay, so just write down your answer. Is a circuit a path? Based on the definition of path, do you consider a circuit as a path? Okay, I see you finished your answer very quickly. What's your answer? Yes. What's the reason? Mm-hmm. Okay. Because a circuit travel different vertices along different edges. Actually, it's just a definition for path. But it's a special case of simple path because the starting point and the end point are the same point. All right, next let's see the definition of Euler circuit. A Euler circuit in a graph is a simple circuit containing every edge of the graph G. Okay, so you need to discover a path contains every path in this graph G, then we call that a Euler circuit. And Euler path is a simple path containing every edge of G, then we call that Euler path. Okay, actually you can discover a lot of different paths in a graph. So if it's use all of these edges in the graph, then we call that a Euler path or Euler circuit. Okay, so maybe we can try these three examples to see if we can find Euler path or Euler circuit. All right, let's see. If we travel from A and then we can go A, B, E, D, C, E, A. Okay, then we just travel each path exactly once and we go back to the initial vertex A. So this is a Euler path. Okay, so maybe we can try G2. For example, A, B, C, D, A, E. Okay, so maybe you can try other ways to see if you can find the Euler circuit. But in this case, it seems not. Okay, so let's see G3. Okay, if we start from A, and then we can travel from A, B, E, D, C, A, D, B. Okay, so that in that case, we travel all the paths in the graph G3, but we cannot go to the initial vertex. So we have a Euler path in G3. Okay, so I hope you can try these three examples by yourself and discover if you can find the rules how to determine or how to discover the Euler path and Euler circuit. Actually, from these three examples, we can see for Euler circuit, if you begin with a vertex A and then you travel along a path, in the end, you need to go back to the vertex A to make it a circuit, right? So that means you need to contribute 2 degrees of degree A because start from vertex A, going out and come along the path and going back to vertex A. So that will be 2 of the degree of vertex A. Okay? And then when we travel the circuit along the path, then it also contributes to all vertices of the path. Because you go into the vertex and go out of the vertex, so that will be 2 of the total vertices of that vertex. And so in this case, we can draw a conclusion. The degree A must be even if we need to discover the Euler circuit. So we need to have a degree A must be even. Then along the path, every other vertex must also have even degree in Euler circuit. Because maybe you can travel the vertex multiple times. But each time you go this vertex and go out of the vertex. And you go in this vertex again and go out of the vertex. So the degree of every other vertex must be even. Okay, so by this observation, we can see actually for Euler paths, we just start from vertex A, but we didn't go back. So the start point, initial vertex, and end vertex, they have odd degrees. Okay, so it cannot be even, right? Because we just start from the initial vertex and we didn't go back. Okay, so this simple observation gives us theorem of sufficient and necessary conditions for Euler circuit. A connected multigraph with at least 2 vertices has a Euler circuit if and only if each of its vertices has an even degree. Okay, so we can see if we have at least 2 vertices, how to discover if we have Euler circuit or not? Because you can see for this theorem we have multi-graph, so maybe we have more than one edges connecting to these 2 vertices. So it tells us if its vertex has an even degree, then we can discover the Euler circuit. It's a necessary and sufficient condition. So we can see if we have vertex A and B, so the degree of A and B are both 2. So we have at least 2 vertices in this multigraph, and each vertex has even degrees. So of course we can discover Euler circuit from A to B, back to A. That will be a Euler circuit. So next we can examine by this simple theorem to see if we can find Euler circuit by the following graphs. Okay, so for G1, we can see the degree of ABCD is 2, 3, 2, 3. Okay, so that means we cannot find the Euler circuit because we need each of its vertices has an even degree. But now we have 2 vertices with degree 3. Okay, so what about G2? 2, 3, 4, 4, 4, 3, 2. Okay. So actually we have 2 vertices with odd degrees, so we cannot find the Euler circuit. So by G3, actually they all have odd degrees. Okay, so next let's see the necessary and sufficient condition for Euler's circuit. If we have a connected multigraph has Euler paths but not Euler circuit, if and only if each of its vertices has exactly 2 vertices of odd degree. Okay, so exactly 2 vertices of odd degree means the other vertices are even degree, right? Okay, but with odd degrees, we only have exactly 2 vertices. In this case, we will have Euler paths, but not Euler circuit. So maybe we can check this example again, because for G1, we have 2, 3, 2, 3. So we have exactly two vertices with up degree. Actually, that's the initial vertex and the end vertex. So maybe we can travel from B, B, A, B, C, D. Okay, so that will be a Euler circuit. Start from vertex B and end at vertex B. Okay, so for G2, actually we have B with degree 3 and D also with degree 3. For the other vertices, they all have degree, even degrees. So we know you can select the B or D as the start or end point and try to discover the Euler paths by yourself. Okay, so by this theorem, actually we can solve the 7 bridge problems because once we transform the regions as vertices and the bridges as the edges, then we can transform the tau and the bridge into this graph. So we have A, B, C, D for vertices, and we have 7 different edges as our bridges. Okay, so if you watch this graph carefully, you can see we have degree for A, B, C, D is 5, 3, 3, 3. Okay, they are all degree, all up degrees. Okay, so by these two theorems, we can see we cannot discover Euler path and Euler circuit by this later term. All right. Next, we will see the algorithm how to construct the Euler circuit if we have a very complicated graph. Okay, we can discover the Euler path or Euler circuit in a very systematic way. Okay, so let's see this algorithm. So maybe we can see this example first, and then we jump to the detailed description of this algorithm. So given the graph G, actually you can see we have a rectangle here and we have a triangle here. So definitely you can have a Euler circuit. So the algorithm tells you can find a simple circuit of this graph by a small connected component. For example, we can find a circuit by this square. So if you travel from C, D, A, F, C, then that will be one small circuit of this figure. All right. Once you can find the connect component as a simple Euler circuit, then we try to remove all edges of this circuit we discovered. And then we put this circuit into a new figure here. So we the main circuit of the new circuit we discovered. Then we remove all edges of the original graph G. Then we generate a new graph H. So you can see in this new graph H, we don't have those edges of the Euler circuit. The first step when we discovered the Euler circuit. Okay, and then based on the graph H, then we can apply the algorithm again. We try to find the Euler circuit in a smaller scale. In this case, we have the triangle here. So we can discover a variance of Euler circuit by this triangle. After we discover this common component, then we can make this component, add this component into the circuit graph. Okay, so that makes the circuit graph like this. And then we remove all edges of this common component. Alright, so it's just like this empty edges. So in this case, we cannot discover any 4 Euler circuits, that will be the end of the algorithm. Okay, so in this case, actually we can travel the triangle to discover the Euler circuit. And then we also travel the triangle and rectangle to find the circuit. So in this case, once you can discover the circuit, then you can start from any point here to complete the traverse of all these vertices. Then that will be the Euler circuit. All right, so if you know this example, then we can go to the algorithm. Okay, so in this algorithm, Euler, we have the input, a given graph G, which is a connected multigraph with all vertices of even degrees. That follows the theorem. We can discover the Euler circuit in this graph G. And then we have the circuit. A circuit in G beginning at and entering through the vertex with edges we add to form a path and return to its vertex. Actually, it's just the definition of circuit. Just find a small scale circuit. And then G with the edges of this circuit removed to generate a new graph H. Because we already found a small scale Euler circuit. And then we remove this circuit from the graph G. Then we can continue a while loop by this graph H. Okay, so you can see in this while loop, we continue to find some circuit within the graph H. And then we remove all those edges of H to discover if we can find more Euler circuits. Okay, and then we still update new circuits into the graph circuit. So when we break the while loop, then we return the circuit. That will be a Euler circuit. All right, any question for this algorithm? So let me invite someone to describe this algorithm in Chinese for everyone. The student with the hat. Okay. Can you repeat this algorithm for everyone? How to discover the Euler circuit? Maybe by this example. Hint. All right. Maybe the girl saying in front of him. Please speak a little bit louder. OK，好，隔壁的同学帮他重复一下他刚刚讲的话，好不好？嗯嗯，原理上是这样哈，但是如果要把它跑成一个演算法的话，要怎么办？就要一步一步做这样。不然就是可能像这样这个情况，就是把它拆成可能两个可以解决它之后，就是这个然后假如说 好好，但记得当你找出第一个路径的时候，你要把这个路径从原本的图里面要拆掉，从剩下的点跟 H 里面去找第二个路径，然后持续找下去，直到找不到为止。好，那 let's try this example and apply the algorithm and draw the Euler circuit by this graph on your paper. So when you write down your answer, you need to show that you know this algorithm. You need to let TA and professor know you know this algorithm. So don't give me the direct answer of a complete Euler circuit. You need to show your steps, how to apply this algorithm to find the Euler circuit. Maybe you can find the Euler circuit by yourself for this graph. But if I give you a very, very complicated graph, for example, 10 or no 10, 100 vertices with more edges, how to discover the Euler circuit in a systematic way. All right. So I hope you finish your answer. So by this algorithm, actually it asks us to find a small Euler circuit. And then based on all these small circuits, we can draw the complete Euler circuit. So let's see how we can discover the small scale of the Euler circuit. For example, A, E, B. Okay, these three vertices we can find a Euler circuit. And then C, B, D, we can find the circuit. And then B, E, F, E, we can find the circuit. And then E, I, F, E, we can find the circuit. So actually you can discover all these small circuits by yourself. And once we can determine all these small Euler circuits, how to draw the final circuit? Anyone want to try this example? By traveling all these small Euler circuits and draw the complete Euler circuit for this graph. So I want to try, I want to draw the Euler circuit, one extra point. Okay. 但是 记得要用小 component 来走，不要乱走，这样。
就是白可以走。
要用演算法走小的 circuit， 不可乱走。好，来这边，帮我看。对。好，比这个。
要换了。就是假如说我从随便一点，从 I 出发。
好，可以。
从 I 出发，然后就这样 I H K G F D。
好，那你换黑板上好了。这边，有，你有画，好。
好。B， 然后 E。
好，继续。
然后 I， 这就是一个图形嘛，就是一个像月亮的形状。然后另外一个就从 I 出发，这样，跑掉了，又跑掉了。I J H G， 然后 D B A E F， 然后再回到 I， 这样，那就一笔画。
好。那个老师再给你一个机会啊。来，我在黑板上给同学看好，这边好像看不出来那个顺序这样哈。好，就是你刚刚是先画一个大的弯的月亮的形状，对不对？好，但是呢，你有没有办法从最小的 component 一个一个画出来？
最小的 component。
对，因为你的大的月亮里面已经包含好几个 component 了。
可以把它拆成这样。
对，但这是大的，你有办法拆出最小的？
最小的。最小的是。
对，没错，没错，好。那你现在从最小的 component 开始画这个 circuit， 你会画吗？
从最小的 component。那就一样从 I 开始。
好。
就 I， 然后 J。
好。
H。
OK，I J H。
对。
然后。
接下来画这个。
好。
H， 然后 G D B C。
H G D B C。
对。然后，不是 C， 是 E。然后 E 再接着画。
好，那我跟你哦，当你走 HG 的时候，实际上 HG 你是要表示哪一个 component？因为 HG 的 component 可以是 HGK， 也可以是 HGFI， 所以你应该要从每一个小的 component 开始去 travel。好，那再修改一下，你开始从 IJH 是那个三角形的吗？接下来你想要 travel 的下一个小 component 是谁？
那就从 HKG。
好，来，那重新改一下哈。IJH， 好，接下来是 HKG， 然后呢，接下来下一个 component 你要找谁？你现在已经有两个三角形了，对不对？所以你现在跟 G 相关的 component 就是有下面这个嘛，GDF 嘛，然后也有 GHIF， 有两个，那看你要找谁这样。
应该从小。
都可以，好。
那个 GFD
好。好 ，GFD，OK。好，那你走到 D 之后呢，接下来要找谁
？DCB。
好 ，DCB。好 ，D 之后就是 BAE 吧。
BAE。
好，然后走到 E 之后呢？
然后再来 EFI。 I 在走 I H。
对，没错，好，到这边就可以了哈。因为如果你在图上面画出来，接下来就会看到每一个 component 就会只剩下最后那个 edge，你就去把那个 edge 走完就结束了，这样。好，这样哈。Alright, next let's see the applications of Euler path and circuit. Actually, we know how to transform different applications into graphs. For example, we have different intersections of the street in the local neighborhood. Then we can transform the street and intersections by the graph. Okay. Or we can also transform the communication links in the computer networks. And then we can discover if we have the path or the circuit. Because that means we can deliver something from A spot to B. Okay. Then we have more applications such as layout of circuits or network multitasking or molecular biology. Okay. That will use the path and circuit problems in this field. Right, next topic, let's see Hamilton path and circuit. Previously, we traveled each edge once in this path. In Hamilton progress, we visit every vertex exactly once. Okay, so we can see a very old puzzles. This puzzle is invented by William Hamilton. So the puzzle is a wooden ball, and this ball is made of 12 regular pentagonals. So we can see this is a pentagon. Once we attach 12 pentagonals to make a wooden ball, then we can have a pad at each intersection of these lines. And then you can attach a string of this pad. So once you start from this point, you can drag the string to other pad. That means if we consider this 12 point as 12 cities, then you can travel each city once. Okay, so that's the puzzle. If you can visit 20 cities once along with the balls, once you can attach the pad and the strings to mark the paths of your visit. Alright? So actually we can transform this problem or puzzle into a graph problem. So consider you put this wooden ball on the surface of the mask. So if you use this pentagonals as the down surface, and you use this pentagonals as the up surface, and then you put the wooden ball on the mask. Right? And then imagine if we can make this pentagon large, so maybe we can stretch this ball to make this pentagon as a larger pentagon. And then you can press this wooden ball downward to the surface of the dust to make the ball as a flat plane. Okay, then we can just make the original 3D graphs on the plane as a planar graph, just like this. Okay, so you can see this is the pentagons in the bottom of this ball attached to the surface of the dust. Pentagon is the up pentagons of this ball. Once you press it down as a plane, the vertex and edges is like this. So we can try to discover if we can visit each vertex exactly once to discover the path or circuit. Then that would be the Hamilton path in Hamilton circuit. Alright, so let's see the definition of Hamilton path in circuit. A simple path in graph G that passes through every vertex exactly once is called Hamilton path. If it is a simple circuit pass through every vertex exactly once, then it is called Hamilton circuit. Okay, so you can see this problem is very similar to Euler path and Euler circuit. If you can travel all the paths exactly once, or all the vertices exactly once. By this example, you can see Hamilton path seems more simpler because if we can travel from A, B, C, D, E, A, travel each vertex exactly once to pass the circuit, then this is Hamilton circuit. How about this one? A, B, C, D. So we can visit every vertex once, but we cannot go back to each of the vertices. So this is an example of Hamilton path. How about this one? A, B, G, E, C, D. So in this case, we cannot visit all vertices. How about F, E, G, B, C, D? Okay, there's always one vertex we cannot visit. So there is no Hamilton path in Hamilton circuit. Okay, unlike Euler circuits, we have two algorithms to help us determine if we have Euler path and Euler circuit in a given graph. But here for Hamilton circuits, we only have the necessary condition for Hamilton circuits. So it's not that easy to determine if we have an even only condition to Hamilton circuits. Here we only have necessary conditions. Let's see the description. A graph with a vertex degree 1 cannot have Hamilton circuits. Because we already know when we travel along the Hamilton circuit, the degree of each vertex must have even degrees. Okay. If we have a vertex with just 1, 2, 3. Okay, that means you can go out of this degree, but you cannot go back. Okay. So in this case, we cannot have Hamilton circuits. Let's see the second point. If a vertex has degree 2, and both edges must be part of Hamilton circuit, because we need to visit this vertex and go out of the vertex. So the degree 2, both edges will be part of Hamilton circuit. Then what happens if we have more paths or more edges of that vertex? For example, we have 4 different edges of this vertex. Then remember, by visiting this vertex, we will use 2 of the degree. So the other 2 edges cannot be used anymore. Because once you use H3 and H4, then you will visit this vertex once. So once this visit is visited, and you use 2 edges to visit this vertex A, and the other edges attaching to vertex A, you cannot use any longer Hamilton path and circuits. Maybe we can see this example by point 1 and point 2. In the graph G, we can see for the vertex E, the degree is odd. We only have degree 1 for E. So in this case, we cannot have Hamilton circuits. Maybe you can try yourself. There's no way you can going back to E. And once you visit E, you cannot go out. Okay, so there's no Hamilton circuits. Let's see the point 2. If we travel from B, A, C, E, okay, then you cannot visit all the edges of vertex C, because you can see from vertex C, the degree of vertex C is 4. But once you visit Okay, so if we visit from B, C, A, B, and we remove these two edges, then there's no way we can calculate hypothesis. All right. Although we don't have a complete theorem, but actually we have two theorems for necessary condition for Hampton circuits. Let's see the Rex theorem. If G is a simple graph with n larger or equal to 3 vertices, such that the degree of every vertex in G is larger than n divided by 2, then G has a Hamilton circuit. Okay, so this is all the conditions. G is a simple graph with the vertex number larger or equal to 3. So this is the first condition. And then we need every vertex degree of G is larger than n divided by 2. Okay, so for example, if we have 4 vertices in G, so it follows, it satisfies the first condition, n is 4. And then every degree of the vertex must be larger than or equal to 4 divided by 2 is 2. Okay, so if you can assure that every vertex has to be larger or equal to 2, then this graph G has a Hamilton circuit. Alright, if you remember the logic, if P then Q, P means the condition, and Q means G has Hamilton circuit. Then what happens if P is not satisfied? For example, if G is a graph with n equals 4, but not every degree of the vertex is larger than 2. Okay, can you say that G has no Hamilton circuits? Remember, we have learned the logic in P and Q, right? Now Q is G has Hamilton circuits. If not P, can we say that not Q? We don't have this logic, right? So we only have the equivalence of if P then Q is if not Q, then not P. But if it is not satisfying this condition, you cannot say G has no Hamilton circuit. If it is not satisfying the condition, then we can only say we don't know G has a Hamilton circuit or not. It cannot be determined based on the Rex theorem. So we call this necessary condition. You need to use this theorem very carefully. Okay. The second theorem is Morris theorem. If G is a simple graph with n larger than 3, we have n vertices. And then degree u plus degree v is larger or equal to n of every pair of the non-adjacent vertices. Then G has a Hamilton circuit. Okay, so maybe we can see what this algorithm tells us. Okay, if we have a graph ABCD, okay, then we know this is a simple graph with n equals 4. Okay, then we can verify if every pair u and v of non-adjacent vertices is not satisfy d of u plus d of v larger or equal to n. In this case, n is 4. Okay, so you need to find every pair of non-adjacent vertices. If we take vertex A, then its non-adjacent vertex with C. So we have the first pair AC in this case. For B, we have BD. And then all the non-adjacent vertices pair, we have only two pairs, A, C, and B, D. And then we can determine the degree of A and C. Actually, the degree of A is 2, degree of C is 2. So 2 plus 2 equals 4. 4 is larger or equal to 4. So the first pair is okay. And for the second pair, BD, the degree of B is also 2, and the degree of D is also 2. So 2 plus 2 is larger or equal to 4. This pair is okay. Okay, so now in this case, given this graph G, actually it follows Ory's theorem. We can apply this theorem to claim G has Hamilton circuits. All right. So lastly, let's see the applications of Hamilton paths and circuits. So if we also consider the intersection of a city and each place pipelines intersect in a utility grid or each node in a communication network exactly once, then we are trying to find the Hampton path. There is a very famous problem which is called traveling salesperson problems. To ask for certain paths for this traveling person that paid to visit a set of cities, and they want to reduce the cost to find the Hampton circuit because when it visits every city once, and we have different costs for the H. One is the circuits with the noise cost. Okay, so you will see this problem in the course algorithm. So you will see more details then. All right, any question for this section? All right, if no question, then we will see section 10.6. We will see shortest path problem. Okay, so if you remember what I mentioned, traveling salesperson problem, actually we have a graph with the cost along the edge. So in this case, we have the graph, we have different vertices, for example, KL, and JB, and then we have the edge connecting different vertices. In this case, we have the weight along the edge. For example, KL to M, the edge number is 1. KL to KB, the edge number is 3. So we call this weighted graph. Okay, because weighted graph is used very common in graph theory or applications, such as airline systems. You can consider we have two different systems, and maybe that will be the distance between these two systems, or the ticket fare of the airline system. So it's very useful to assign weight to the edge in this graph. Right? So the problem we are trying to solve is to find the shortest path problem. So the shortest path problem involves smallest life time. If we label the time cost for h, then you can see how you can travel along a path to have the minimum traveling time. You can also label the cost as fare. So shortest path problem will be to discover a path of the airline system to give you the cheapest fare. Okay, so maybe fastest response time or shortest distance. So that all can solve by shortest path problem. All right. For traveling salesperson problem, actually we are trying to discover a circuit with shortest total length that visit every vertex of a complete graph exactly once. Next, let's see how we discover the shortest path. Okay, so let's see this example. What is the length of a shortest path between A to Z in the given weighted graph? Okay, so we have a graph here. Then we want to find the shortest path from A to Z. Okay, so actually you can discover all possibility of the paths. Then we calculate the cost for each different path. For example, you can travel A to Z by A, B, C, is a path from A to Z. And we can calculate the cost A to B 4, B to C 3, C to D 2. So the total cost will be 9. But because we need to find the shortest path, so we need to discover all paths between A and Z. So we have A, B, C, Z. We can also travel A, B, E, Z, or A, B, E, Z, or A, B, E, B, C, Z. Okay, so in this case, we have 4 different possible paths. So the length will be 9, 8, 6, 8. In this case, we can choose the shortest path, the length 6, by A, B, E, Z. A, B, E, Z. Okay. 2 plus 3 plus 1. So that will be the shortest path of the length 6. Okay, so this will be easy, but when this graph has more vertices, more edges, how we can apply the algorithm to help us to discover the shortest path? So next, let's see the algorithm, Dijkstra algorithm. All right, we will see how to apply this algorithm to discover a shortest path of a given weighted graph. All right, so this is an iterative algorithm. Let's see different iterations, how we discover the shortest path. Okay, so initially, we know the initial vertex is A, and the end vertex is Z. So initially, we update the path length for infinity for every other vertex. Okay, because now we are not traveling yet. We don't know what is the length of the path. So we just give infinity for every vertex in this path. Alright? And then in next iteration, we start to travel from vertex A. So we give a circle to indicate now vertex A is already included in the shortest path set. Okay? And then once we have the first vertex in the shortest path set, then we can update the path because A can travel to B and A can travel to C. So now we can see we update the path of AB to 4. And we label if we come to vertex B, it's originally from vertex A. And we also update the path of the vertex C. This is shortest path from A to C. The path length is 2. Now we can see, actually we are traveling from A, and we try first pass AB, second pass AC. In this case, we have the shortest pass to C, right? Because the pass length is 2, the other pass length is 4. So 2 is the minimum length. In this case, we include the vertex C into our minimum shortest path set. Now we have the set with the vertex A and C. Right? And then we try to go one step, then we should see how we can update the length as another minimal number. Okay, for example, we can reach it from C by one step. Okay, Okay, so if we travel from A, now the length is 2, then we travel to B, then CE is 10. So the total length will be 2 plus 10 is 12. So we just record this is the only way we can reach P from our minimal Chebyshev set because we have AC. Only C can reach P, A cannot. Okay, so this is the only number we can calculate from this set. So we update the length of E as 12, and we record on the path now is AC to the vertex E. Right? And then we can see how we can reach other vertices on the set in C. Okay, now we can see for the vertex B, we can travel from A, B. We can also travel from C, B. So let's see how we update for the minimum distances. Originally, in the previous step, A to B is 4. But now, if we can reach B from C, then the path will be 2 plus 1 will be 3. So we update the path of the vertex B to 3, and we record the path in C. Okay, so now we have just only one vertex we can reach from the set AC. That will be E, because we have an edge from C to E. Alright, so we know now the middle path for C is 2 plus this vertex, plus this edge of 8. So the length will be 10. Then we record AC because we reach from the vertex C. Okay, so you can see originally they are all infinity, but once we can include other numbers into this table distance set, then we can update the length for other vertices. So in iteration 3, we can see Z remains infinity because we cannot reach Z by the set A and C. So for Z, the distance is 0. Now we can check which one we should select into the set. Because for B, number 3, for D, number 10, for E, number 12, for Z, so to choose the vertex with minimal distances, the next candidate we choose B. So now we give B a circle to indicate B is already included in the minimal vertex set. Now we have ABC in the set. Then we use ABC to update the distance or length of the vertex. So let's see. Okay, so actually B can be reached by B or C. Okay, and in the previous step, B is 10 from C. So now we can verify if B can have smaller lengths starting from B. So now we know the length of B is 3 and B is 5. So 3 plus 5 is 8. Length 8 is smaller than the distance 10 in the previous situation. So we update length for B. And then we record the path. B is originally from AC. So now it will be AC to the vertex B. So that's how we update the length of B. Now we can see what happened to vertex C. Okay, so we can see, although we have ABC set, but only C can reach G. So we don't have to update because there's no change. Once we include B in the set, E cannot reach B, so we remain the distance from E as 12 and Z for infinity. Alright, now we have only 3 candidates. B is 8, E is 12, Z is infinity. So to choose the minimal length, then we choose the candidate D in this case. So then we give a circle to indicate D is already chosen into the minimal Then we can try to update the vertex E and C. Okay, so now we can see E can be reached by B and C. So we need to check which gives us the shortest path. 2 plus 10 is 12. 8 plus 2 is 10. Okay, so we know we have the shortest path from E to E. That will be the shortest path. So we update the previous 12 down to 10, and we report the path A, C, B, D. Okay, and we call this path to the vertex E, and update the length to 10. And then now we can finally reach Z. So 8 plus 6 will be 14, and we report the path A, C, D, for the vertex E. Okay, now we have only 2 vertices, and the length will be 10 and 14. Okay, so now we include the vertex E into our set. Okay, now we have the final step because we have the distance for Z. Now we include the vertex E. Then we need to check if we have even shorter paths from E to Z. So we know the length to E is 10. 10 plus 3 is 13. Okay, so 13 is smaller than 14. So we update the length to Z by length So now we have the final vertex Z. We can include Z into our minimum set. Then now we have our final vertex included in this set. That means the end of the algorithm. So in this case, we can find the shortest path. Actually, how to travel from A to Z? We need to travel A, C, B, E, E, C. That gives the shortest path. So maybe we can verify this a little bit. A to C to B to C to B 1, so that will be 3. And B to E 5, that will be 8. P to E will be 2, and that will be 10. And E to Z will be 3, that will be 13. Actually, we record every step along the path. So you can see it is easy to verify on this path, the length will be 13. All right, so let's see this. Do we need to see the algorithm? Because it just followed the same step in our previous step. Okay, so maybe let's try this example to see if you understand this algorithm or not. Okay, find the shortest path from A to Z and try to discover the path by yourself using the Dijkstra algorithm. Alright, next, let's see how to apply the algorithm by this example. Okay, so from A to Z, okay, so initially we just update the distance for all vertices, and it will be infinity, right? Infinity initially for all vertices, and 0 for the vertex A. And then we include A into our set. And then once A is in the set, then we update all vertices by its different lengths. For example, B, so you can see the distance is 2. Okay, so we update the distance from A to B is 2. And we record the vertex A for this length 2. And then for C, the length will be 4. It's from A. Okay, now we have 2, 4, infinity, infinity, infinity. So the minimum length will be B, right? So we include B into the set. Now we have A and B. So B can reach CDE. So we need to check if we have even shorter lengths for CDE. Okay, let's see. Originally C is 4, but if it goes from B, then 2 plus 1 is 3. And we will have a shorter distance as 3. So we update 4 by 3. And we record this surpass A to B to C. Okay, and then for D, D can only reach by B, so we need to check 2 plus 4 is 6. Okay, now the distance to D is 6, and it goes from A and B. And for E, 2 plus 2 is 4. Okay, so we change infinity to 4, and it travels from A to E. Okay, now we have 3, 4, 6, and infinity. So we choose C as our next minimum step. Okay. Once C is chosen, then we only need to check if we need to update the weight of the distance of E. So 3 plus 3 is 6, but the original distance is 4. So we do not need to update the distance of E. So we remain as 4. Okay. Now we have 3 vertices, 4, 6, and infinity. So we include the vertex E into our set. So once E is included in the set, then we need to update the distance for D and Z. So now we have 4 plus 3 is 7. 7 is larger than 6. So we don't need to update the distance for D. And for Z, 4 plus 3 is 7. So we change infinity to 7 and record as ABE. Now we have 6 and 7, so we include the vertex D into the set. And then we update the distance. 6 plus 4 is 10. 10 is larger than 7, so we don't have to update the distance. Okay, now we have only the final vertex we can include into our set. Then we have discovered the path from A, B, E to Z, and the distance is 7. All right, any question for this algorithm? Okay, if no question, then see you on Thursday.
完全没感觉。解决危机了。他修好了，都修好，都修好。上面就这条。这个是一把钱。先把股票买一下，然后把卖掉。预设加到底。哪困难？你是之前交期的，你说你七都没有，一天可能一天没有提到。因为我们这个很早期就这是你可以讲的。我们秉持大家是善良前进的一个。但是要怎么记录这件事？对不起啊。我相信我会烧死。到时候会看到。到时候会看到。没看到你再说一下，因为有可能我们忘了。就是到时候如果你的成绩被算迟下的话，你可以过来说一下，直接自己说的。应该是吃饭。他在外面如何？